It's now a pleasure, as usual, to introduce the moderator of our next session, which is Dr. Bruce Betts, the Director of the Planetary Society. Thank you so much.
Now we move from the world of science fiction to the world of science that sometimes feels like fiction in terms of the discoveries. If I could get excuse me class, if I could get a little more attention, please. Thank you. We've had 3 missions that in the last year have given us amazing discoveries and amazing engineering feats. We will have representatives from all 3 missions talking here this morning. One intentionally slammed a spacecraft into a comet at 10 kilometers per second to find out what the subsurface was made of. One brought samples back successfully from the coma of a comet. And one performed the first ever orbital activity and sample return activity at an asteroid. Orbital is technically incorrect as the first. All of them very, very interesting. So, without further ado, let me get into our speakers. Our first speaker comes from JPL. He is Don Yeomans. He is one of the world's experts on near-Earth objects, one of the go-to guys when trying to figure out whether an object out there is going to be dangerous. And he is also a well-respected, well-renowned scientist who is involved as a co-investigator on many of the missions out there right now, including the ones being talked about. But in particular, he's going to talk to us today about the Deep Impact mission. Please welcome Don Yeomans.
We're going to talk to you this morning a little bit about comets, and I'm going to introduce the topic by pointing out that comets are important scientifically because they're leftover bits and pieces from the outer solar system formation process. So if we wish to study the mix from which the outer major planets formed, we'd like to study the comets because they haven't changed a great deal in the last 4.5 billion years. You probably all know the basic makeup of a comet. I'm just pointing out that there are gas tails that are pushed away in the anti-solar direction. There are dust tails that are pushed away by the pressure of sunlight. And the nucleus of a comet, which is what we want to talk about in the next 2 talks, is effectively hidden by Mother Nature whenever a comet gets into the inner solar system, because the ices on board the comet start vaporizing and releasing the dust particles, and it forms this enormous atmosphere that effectively hides the heart or the nucleus of a comet. So you have to send spacecraft. Now, if the Earth runs through some of these dust particles, most of them are the size of grains of sand, you get meteor showers or shooting stars from time to time, especially in August and November with the Perseids and the Leonids. And about 100 tons of this dust comes down to the Earth surface on a daily basis. And if you include the rocks the size of basketballs and Volkswagens, that number gets up to around 400 tons of material settling down on the Earth's surface on a daily basis. So we are daily hit by near-Earth objects. There's no question about that. In the outer solar system, the folks doing the damage are comets, because that's where they formed, and the asteroids are in the inner solar system. Any of the outer planets that has a satellite without an atmosphere to protect it is covered with impact craters from comets. This is Saturn's moon Mimas. And any of the other satellites out there that don't have this protective atmosphere will have the same type of celestial divots, mostly due to comets. Of course, the comets can hit the Earth as well. This is a video or an image from the Deep Impact movie. It's clear that when you get to the larger and larger objects, you get fewer and fewer of them. And so these large impacts by objects that are a few kilometers in size don't happen very often, but when they do, it's very serious, of course. And it's been pointed out more than once that an impact some 65 million years ago, probably by a comet, caused the demise of the dinosaurs, the acid rain, the raising of the dust into the atmosphere to shut down the sunlight, all of which destroyed the dinosaurs some 65 million years ago. Mind you, there are alternate theories for the death of the dinosaurs. Some folks think that volcanic activity is responsible, and some folks think the diet was responsible. This is my favorite alternate theory. It's also important to point out that comets likely provided much of the water and carbon-based molecules to the early Earth once the late heavy bombardment let up some 3.9 billion years ago. And so comets may have delivered to the early Earth much of the water and the carbon-based molecules as a veneer on the Earth's surface. And of course, those two ingredients are absolutely necessary for life. So in some sense, we're all made of cometary stuff. Without them, we wouldn't be here. Without them taking out our principal competition some 65 million years ago, the dinosaurs, and that allowed the mammals, who at the time were just furry little creatures burrowing under the ground, it allowed them to reach the preeminent position that we now enjoy atop the world's food chain. So we do owe a great deal to comets. The cometary nucleus, as I pointed out, it was a mystery until fairly recently. The first spacecraft to actually image a cometary nucleus was in March of 1986 with the European Space Agency's Giotto spacecraft. And when trying to understand what a cometary nucleus might look like to the Giotto spacecraft, we thought of, well, all right, we knew that comets were dirty ice balls. We knew that ice balls were fairly good at reflecting sunlight. And so the Giotto camera was actually programmed to view the brightest object in its field of view. It had to be done autonomously, of course. So the Giotto camera was actually programmed to follow the brightest object in the field of view. The comet, of course, turned out to be the darkest object in the field of view. And the artist's conception is at the top. The actual image of the comet Halley is at the bottom. And you'll note that in the upper left-hand side, you have higher resolution from the imaging because that is where the camera pointed. Not because the comet was the brightest object in the field of view, but because the dust particles that were coming off the comet at that point did scatter the sunlight rather effectively, and that was the brightest object in the field of view at that point. So, Mother Nature 1, scientists 0. On that score, we got the initial estimate of what a cometary nucleus might look like wrong. Then we went into a decade of cometary exploration. We had the Deep Space One spacecraft fly by Comet Borrelly in 2001. We had the Stardust spacecraft fly by Comet Wild 2 in early 2004 and bring back a sample in January of this year. In the next talk, we'll speak to that in some detail. We had the Deep Impact spacecraft actually run into a comet on July 4th, our nation's birthday of 2005, and I'll get into that in just a moment. And then the European Space Agency has now in flight a spacecraft to actually orbit and land upon the short period comet Churyumov-Gerasimenko in 2014 rather. This is the image of Comet Borrelly as seen by the Deep Space One spacecraft on September 22nd, 2001. It's being rocked back and forth artificially so you can see the surface detail. It looks a bit like an old sneaker, so I think we found Bigfoot. It's out there. The image resolution was about 48 meters, about half the size of a football field, and about twice the image resolution of the Giotto spacecraft. This is the stereo pair of Comet Wild 2. And again, the next speaker will get into this mission in considerably more detail, but I just note that the image resolution is again half of what it was on Borrelly. And as you get higher and higher image resolution, you get more and more detail. And this left foot and right foot that you see on the image here is interesting in the sense that it's about 100 meters down from the surface. And what that means is that one of the things that means is that you've got a surface that's very, very weak. It's like a weak souffle, or perhaps the foam on a cappuccino. You've got a very weak structure here, and that's one of the things that's coming out of these cometary missions. Now, the Deep Impact mission itself, the PI is Micah Hearn from the University of Maryland. The mission partners were JPL, did the navigation and management. Ball Aerospace built the spacecraft and instruments. And of course, the objectives of this mission were to study the composition and structure of a cometary nucleus as a function of depth below the surface, and to infer the nature of the comet's interior. Is a monolithic dirty ice ball, a low-density icy dirt ball, a pile of chunks of 100-meter-sized objects held together by little more than their own self-gravity, or some sort of a wimpy, fragile fluff ball, which in fact turned out to be considerably closer to the truth than the others. And some other objectives were to try and understand the chemical composition of the ices. It was mostly water ice, as it turns out, carbon dioxide, carbon monoxide, hydrogen cyanide, and lesser ices as well. But this was one of the preferred models of the cometary nucleus before we got there. It was sort of a homogeneous dirty ice ball covered by a crust of material, organic material, carbon-based material that was laid down on the surface. And so the comet's interior ices would only be exposed to the sun when the comet rotated those cracks in the crust toward the sun. So that was one of the preferred models. That didn't turn out to be correct. Another preferred model was the so-called rubble pile, where you have 100-meter-sized chunks of dirty ice held together by little more than their own self-gravity. And so these two models were probably 1 and 2 in terms of what we expected. Of course, once again, Mother Nature pulled the wool over our eyes, and it was Mother Nature 2, Scientist 0 in terms of the cometary nucleus. The Deep Impact spacecraft was, the impactor itself was 370 kilograms, much of which was in the form of a copper slug. Copper was selected because we didn't really expect copper to be in the comet itself, and it was a lot cheaper than gold. So we needed something heavy, cheap, and not expected to be part of the cometary composition. The flight time was relatively quick, 6 months. We put the spacecraft in front of the comet and let the comet run over us at some 23,000 miles per hour, releasing the equivalent energy of 4.5 tons of TNT. This is actually an animation by Dan Moss showing what we expected to see. That's the high-resolution imager, the large telescope on board the mother spacecraft. 24 hours out, the mother spacecraft actually released the impacting spacecraft and then maneuvered. Here's the release of the impacting spacecraft. They're completely autonomous at this point. There's no ground controlling or joysticking from the ground allowed. We don't have time to do it. So this is a very smart spacecraft. It's got its own camera system, its own thrusters, its own computer to zero in on the comet itself. Now the mother spacecraft actually slowed down to follow the impactor by 15 minutes and moved to the side so it too didn't hit the comet. So the impact itself, this is what we expected to see. Large chunks of material coming off the surface, and so that we could actually see through this material and notice the size of the crater being formed. That didn't turn out to be the case either. Okay, so the question was, the nucleus structures was going to be determined by observations from the cometary impact process, and the following scenarios were considered most likely. Case 1, the nucleus is without much internal strength. It's very weak. You can break these materials apart with your hands. The crater formed relatively slowly. About 75% of the ejected did not escape, but actually settled back down on the surface. And the crater would be relatively wide and shallow. And so the analogy here might be that the crater formed as a result of a bullet being fired into sand. The second case that we thought might happen was the nucleus material is weak, but will compress as a result of the impact. So you'd have a rather small crater forming, very little ejecta, sort of like a bullet into styrofoam analogy. And finally, the least likely scenario would be that the cometary nucleus was strong, solid ice, in which case you would have a very fast impact crater forming. You would have a flash of light And the analogy there would be a bullet into solid ice. That did not turn out to be the case. Case one was considerably closer to the real situation than any of the others. Okay, now when the impactor was released 24 hours out, had the impactor not done any course corrections, it would have hit the comet, but on the dark side of the nucleus. That's the pre-release point that you see up there. After the first maneuver, we actually had the spacecraft missing the comet down below there, the post-ITM-1 position. After the second maneuver, we were on the comet, but not exactly where we wanted to be. And after the third maneuver, within 24 hours, we were exactly where we wanted to be, on the sunlit side of the nucleus, and on the side of the nucleus that is closest to the flyby spacecraft, which is going underneath this nucleus at some 23,000 miles an hour. This is actually, the image is of the impacting spacecraft just before it vaporized itself. It actually impacted right between two impact craters. And this is the dust that was released. Micron-sized dust particles, no chunks, particles the size of those in cigarette smoke. Very tiny particles, and they so effectively scatter sunlight that we didn't really get a good look at the crater that was formed, although by modeling, it suggested that the crater was about 100 to 200 meters in diameter, fairly shallow, formed in about 5 minutes, all of which is indicative of a very, very weak, underdense, and porous material. This is an interesting shot. You'll notice the vaporization, or the hot flash, that occurs just before the cloud of dust arises. Let me back it up and try it again. What you're seeing with that vaporization, the eyebrow-shaped poof that comes off first, is one, the spacecraft vaporizing, and two, some of the cometary material that's very hot and also vaporizing. But let me back it up. Okay, you have the hot flash followed by the expanding dust plume. All right, this is the image composite from the impacting spacecraft before it destroyed itself, of course. And so you've got a very peculiar looking object here in a number of ways. You've got very old surfaces, evidenced by the impact craters down at the bottom there. Again, the impact itself occurred right between those two impact craters. And so by analyzing the size and number of these craters, you can determine that the surface, at least at that point, was tens of millions of years old. And next door to it, you've got a very smooth area, which I call the landing strip there. It has no craters in it whatsoever, so that's a very young area. So you've got a very young region adjacent to a very old region. So you've got to try and explain that. So one of two things is likely happening. Either a jet from the comet's icy surface is actually releasing dust particles that preferentially settles down on the smooth area, or perhaps more likely, that smooth area is mostly volatiles and it's a scarp that's retreating as those volatiles or ice is vaporized. So that smooth area could well be a layer of ice and dust that's actually retreating, revealing the more ancient cratered surface underneath. I think that's likely the more, it's probably the more likely situation. The bulk density is about 0.4 grams per cubic centimeter. This thing would easily float if you had a large enough pan of water. The porosity is 70%. It's 70% void. So you're talking about an object that is indeed very weak, very underdense, very porous. And of course, it's blacker than charcoal at about 4% albedo. This is a deconvolved high-resolution color image showing the bits of ice that were actually found on the surface. Not much of the ice, although it's 30% ice all told. The comet is 30% water ice. Only a very little bit of it is on the surface. And from the thermal inertia measurements, the measurements of the temperature of the comet all over the surface. We can back out the information that the subsurface ices must be just a centimeter or two below this talcum powder-sized silicate dust particle. So you've got a very thin layer of dust covering a fairly substantial amount of water ice. And so that was a bit of a surprise. We thought there would be more ices on the surface. In addition, there's nothing homogeneous about this object. I mean, you would expect a comet would form in one region of the outer solar system from material that was fairly uniform, fairly homogeneous. You would have the same amount of carbon dioxide, carbon monoxide, water. That didn't turn out to be the case either. From the spectral observations, we took one spectra in the north, one in the south. That's the dotted boxes over on the right there. And you can see that the spectrum from the north, which is the black curve, is quite a bit different from the spectrum in the south, which is the red curve. For example, in the south, you've got more CO2, carbon dioxide, coming off than you do in the north, which is mostly water. That was a surprise. And this was the money shot. When I was doing the NASA announcing of the mission itself for NASA TV, for the 2 or 3 people that watch NASA TV, I had this prepared speech all set because I was almost convinced myself that we were going to see the spacecraft simply bury itself in the comet, and then I'd be left to try and explain, well, we have word from the navigators that we hit it, but you can't see the results because the spacecraft simply buried itself in this very underdense comet. But when we got this image on the screen, there was no question that we actually hit it, and hit it precisely where we wanted to. So that was the money shot. Okay, so the new paradigm for comets is they're weak, they're porous, they're very black, icy dust balls. Talcum powder-sized silicate dust covers the surface. About 30% ices, mostly water, just below the surface dust. Fairly recent resurfacing and few impact craters. And the resurfacing could be due to these dust jets that are laying down material over the craters, or perhaps more likely, the scarp is actually retreating, revealing the underneath much older cratered surface. There's some evidence that at least this comet does not have a uniform composition. It has more carbon dioxide in the south than in the north. And as recently as 5 years ago, cometary nuclei were thought of as dirty ice balls. Well, that's been revised somewhat by the Deep Impact and Stardust missions to suggest that they're really a weak, very weak, porous, and very black, icy dust ball. It's a subtle difference, but it's an important one. And so, in summary, cometary nuclei are the fragile, jet black, oddly shaped, icy dust balls, and the remnants of the early solar system formation process. They likely delivered to the early Earth much of the water and the carbon-based molecules that allowed life to form. And so we are, in a sense, all made of cometary stuff. At a distance of 83 million miles, the Deep Impact spacecraft, without any help from anxious ground-based controllers, successfully navigated itself and rammed a cometary nucleus at some 23,000 miles per hour. While another deep impact spacecraft flew closely alongside and recorded the events. In a way, these complex and smart spacecraft are our intrepid explorers, extensions of ourselves, and a fine example of the type of gutsy exploration that is right on the edge of what is doable and what is not. Yes, we humans may be made of cometary stuff, but this instinct to explore and to push the limits of what is possible is part of what makes us truly humans. Thank you for your interest.
We'll take 2 questions. Rusty Schweiker.
Don, you just mentioned two things of interest to me. By the way, congratulations for the great job on Deep Impact. And for the terrific commentary on NASA TV. Yeah, Nancy and I were listening too. The questions are two, and they both come out of what you said. What was the relative velocity of impact? And number two, you said you hit right where you wanted to. What does that mean? You said precisely where you intended. I take it the intention was sunlight and toward the flyby spacecraft, but was it more precise? Was the target more precise than that? And how close did you come to that target if you did have a precise one?
Well, yeah, you put your finger on it. The auto navigation was designed to first head for the center of brightness of the cometary nucleus, and then to refine that to actually head toward the closest region that was still in sunlight to the flyby spacecraft, so that we had to hit in the south and in the sunlit region, so that the flyby spacecraft could get high-resolution images of the cratering. So I think it's fair to say that we hit within a few hundred meters of where the nominal impact was supposed to go. So that was an essential bullseye for navigation, considering that there was no joysticking. Autonomous nav worked flawlessly. And then, as you well know, augurs well for mitigating near-Earth objects that may well be on an Earth impacting trajectory. So we've shown that we can smack them and use the kinetic energy deflection technique at the same time. The relative velocity was 23,000 miles an hour, or 10.1 kilometers a second. It's about 20 times faster than a bullet from a high-speed rifle.
Mission after the impact of the Temple 1 comet is supposed to have do a flyby of Temple O2, but it's supposed to have maybe like some more research. It's also kind of fascinating because my last name is also OT. What is the status of that? Or did you get the funding for that? Or did you get the question?
Yeah, that's a good point. The spacecraft, the flyby spacecraft is healthy. The impactor is vaporized, of course. But the flyby spacecraft is healthy and can be, and may be, retargeted with an Earth swing-by to go by this comet both in a few years. But that has been submitted as a discovery proposal to NASA headquarters, and it's in a competition with a number of other excellent missions, so that if it's selected, that is a distinct possibility. In fact, the Stardust spacecraft is also healthy and could go on to another comet as well. So those are two competing proposals that have not, neither of which has been funded yet.